Please welcome Mike.
Thank you very much, Terry, and also I want to thank Mary Alice Rennick for facilitating me being here today. And I want to thank everyone for coming. I see a lot of familiar faces out in the audience here. That's really good to have you here. So the topic is offshore wind farms and the Morro Bay project. Let me show you a quick outline of what we're going to be talking about today. I'm going to start out talking a little bit about climate change to motivate the idea of offshore wind, then get into the technology of offshore wind power, talk about the specifics of the planned Morro Bay wind farm. Then I'm going to present possible issues of concern. I need to tell you something up front, and that is, I'm a proponent of this project. I hope it goes forward. I've looked at the positives and negatives, and I've come to the conclusion that I believe it should move forward. But everyone may not come to the same conclusion, and I promise to be an honest broker and talking about both the positives and the negatives of this project. I also need to tell you up front that I have no connection to this project. I don't work for any of the companies that might be bidding on this project. I have no interest in working with those companies. I'm interested in climate change. I'm interested in the role that offshore wind can play in dealing with climate change. So that's my main interest here. You'll have a summary and a question and answer period. So climate change and the need to move to green energy. There's an overwhelming international scientific consensus on the following 3 points. Over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. But global warming and resulting climate change over the past 120 years have been driven almost exclusively by the Earth's greenhouse effect and the accumulation of greenhouse gases in the atmosphere caused by human activities. Without dramatic reduction in emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. So stated simply, it's happening, humans are causing it, and it's not a good thing. Now there isn't a legitimate science organization in the world that would disagree with those 3 points. The science is settled, it's been settled for many, many years, and it's very clear. And here's an example. These are leading science organizations that have made formal declarations confirming human-induced global warming, including the U.S. National Academy of Sciences, the U.S. National Research Council, all the organizations that are involved with meteorology and oceanography, such as the American Meteorological Society, American Geophysical Union. The science is settled on this matter, and it has been in 40 years. So what are the consequences of climate change, global warming and climate change? Well, I'm just going to hit the high points here. These are the impacts on the natural world. Increasing frequency and intensity of severe storms. Increasing frequency of life-threatening heat waves. Increasing frequency and intensity of floods in wet regions. Increasing frequency of droughts and wildfire in dry regions like our region. Decreasing mountain snowpacks and earlier snow melt. Rising sea levels. Increasing mortality of coral reefs. Decreasing productivity of fisheries, and loss of biodiversity. So those impacts on the natural world translate into impacts on the human world. And again, I'll just hit the high points. Increasing economic costs, increasing competition among nations for water and food, increasing displacements of people leading to unrest, increasing threats to human health, increasing human mortality from heat waves, other severe weather events, starvation, disease, and war. Not a pretty picture, and we're living that picture right now. So, what are the greenhouse gases that are causing all this problem? Well, here they are listed in order of how much impact they have. Carbon dioxide, methane, the fluorinated gases, or F gases, for example, refrigerants, and finally nitrous oxide. Now, what you see from this is that carbon dioxide, CO2, is the dominant greenhouse gas. It produces more global warming than all the other gases combined. Now that doesn't mean the other greenhouse gases aren't important. They are. We have to worry about them. But carbon dioxide really is the main culprit, and that's the one we really need to focus on most. So let's take a look at CO2 in the atmosphere. This is a plot of carbon dioxide in the atmosphere from 1700 to 2019. And it's measured in parts per million. Before the Industrial Revolution, CO2 in the atmosphere was pretty steady at about 280 parts per million. And then, beginning with the Industrial Revolution, and particularly ramping up in the 1960s, the CO2 levels really started to rise. Right now, we're running at about 419 parts per million. That's an increase of 50% over the pre-industrial level. It's also the highest CO2 in the atmosphere has been in the last 4 million years. Now, from 1850 to 2018, the total amount of CO2 emitted by human activities amounted to about 1.6 trillion tons. Not billion, trillion, 1.6 trillion tons. And about 0.9 trillions of those tons are still in the atmosphere. The current rate of CO2 emission as a result of human activities is about 40 billion tons per year. So where's all that CO2 coming from? Well, by country, China's number one, US is number two, then it's India, Russia, and down from there. So let's take a look at the US. Where's the CO2 coming from in the US? Well, it's mainly from these three sectors: transportation, electrification of the power grid, and industry. Now, the issue of interest today has to do with electricity generation. So in the US, this is how how electricity generation breaks out. This is not representative of the world, this is representative of the US. And about 40% of electricity comes from natural gas, about 20% from coal, about 20% from nuclear, and about 20% from renewables. So the issue of interest here, of course, we're trying to bring down the use of the fossil fuels, natural gas, and coal. Nuclear has its own set of problems. We can talk about it later if you want to. But what we're really trying to do is grow this 20% of renewables. So how does that break out? Well, it's wind, hydroelectric, solar, biomass, and geothermal. Wind is number one. And most of the wind power in the U.S. and in the world, in fact, is onshore wind power. But our topic today really is offshore wind power. That's what the Morro Bay project is all about. So now we'll jump in on that, offshore wind power. Begin by showing you a resource map of wind energy in the U.S. And the way you read this is there's a scale over here, this color scale. It runs from fair to superb for how good the wind is for producing offshore wind energy. Now, this is not a map of wind speed. It's sort of a map of where the wind is optimum for wind energy. You don't want the wind too strong, you don't want the wind too weak. And most of all, you want the wind to be consistent and very steady. And what you see from this map is that there's a lot of wind energy off the coast of the U.S., including off the coast of the West Coast. Within our EEZ, our exclusive economic zone, which extends out 200 nautical miles, as a practical matter, wind farms need to be within about 50 nautical miles of shore. Now, if fully developed, the offshore wind power available to the U.S. would produce about twice as much electricity as we currently have on the power grid. So there's a heck of a lot of energy out there to be had. So let's talk about wind turbines, offshore wind turbines, beginning with some terminology. This is what an offshore wind turbine looks like. And this is the blade. There are three blades on these things. This is the hub where the blades come together. This structure here is called a nacelle. That's where the generator and all the electronics and so forth is housed. This is the tower. This is the substructure, which holds up the wind turbine. Air gap refers to the distance between the bottom of the blade and the surface of the water. So let's look inside the nacelle. This is what a modern offshore wind turbine looks like. A couple things to highlight here. On the top of the nacelle, there are meteorological instruments that measure the wind speed and the direction of the wind. And based on that, there is something called the yaw assembly, basically an electric motor down here, which makes the wind turbine turn. It turns into the wind. Its electric motor turns into the wind based on what the wind direction is observed up here by this wind vane. As the wind speed changes, there is a pitch system. Again, it's an electric motor, which changes the pitch of the blades. That's sort of the twist of the blades, how much wind they catch. And when the wind gets too strong, they can actually feather the blades, which means they reduce the pitch to zero, and there's also a braking mechanism that can be engaged to stop the blades from rotating. It's all done automatically, by the way. There's no human intervention here. There's a computer on board that the wind turbine does all this automatically. The modern offshore wind turbines are direct drive. What that means is there's no gearing system to change the speed of rotation, but rather the generator is housed within this assembly right here. It's just a big drum. The inside of the drum remains fixed in space, and that has coils of wire. The outside rim of the drum rotates with the blades, and there are very, very powerful fixed magnets that are orientated like this, and as those magnets spin around the copper coils, that generates electricity. That electricity comes out as direct current, and it's fed back here to the power converter and system controller. There it gets turned into 60-cycle 3-phase alternating current, just like we have in our homes, except at very high voltage. 66,000 volts is the standard for offshore wind turbines. And then the power is transmitted down the tower and into a sub-assembly. We'll talk about that in a minute. So that's kind of what it's all about there. And here's sort of the evolution of wind turbines from 1980 to 2030. Depicted on the left-hand side of this chart are onshore wind turbines, like the ones you might find up the Salinas Valley. We pretty much hit the limit on onshore wind turbines. And the ones like the Salinas Valley are kind of at that limit. They're 2.5 megawatt turbines. By the way, I'm going to be throwing this term megawatt in a while, so let's talk about that. Megawatt means 1,000,000 watts of electricity. Now, you think about your bulb and your light bulb is in your living room. It might be 100 watt bulbs, 100 watts. Now we're talking about 1,000,000 watts, a megawatt. The best way to kind of put that in reference is 1 megawatt is enough electricity to provide the needs of about 650 average-sized homes. So whenever you think of the term megawatt, think 650 homes, because that's what it would do. So the upper limit right now for land-based turbines is about 2.5 megawatts. That's kind of the size of one you find down at Greenfield in the Salinas Valley. Why is that? Well, it gets to the point where they can't transport the blades on land anymore. The blades are so long that that's about the limit of how far, what the size you can transport on land. No one's figured out how to make blades in more than one section. You have to make one contiguous piece of material because they undergo a lot of stress. And so we pretty much hit the limit on the size of land-based turbines. And it turns out that bigger is better because the amount of energy that a wind turbine produces is proportional to the area of the rotor swept area, which is basically, think about the blades going around. And that's the region there. The energy from the turbine is proportional to that area. Now, going back to your high school math, remember that the area of a circle is pi r squared, right? Well, in this case, the r is the length of the blade. So as you make the turbine bigger and you make the blade longer, the power goes up dramatically. If you double the size of the turbine, double the size of the blade, you don't get double the power, you get 4 times the power, because 2 squared is 4. Increased by a factor of 3, you get 9 times the power, because 3 squared is 9. So we've reached the limit of how big land-based turbines can be made. So that's part of the motivation for going to sea-based turbines, because they are huge. The way they can be huge is the blades are transported by sea. They're not transported by land, they're transported by sea. You have the factory that builds the blades right at the seaport. And when the blade is finished, you roll up the factory doors, and there's a ship right there, and you move it about 50 yards, put it on the ship, and then take it where it needs to be. So these are what the offshore wind turbines look like. The Morro Bay project is probably going to be up in this range. I'm assuming about 14 megawatts, but it could be larger. It could be around the range of maybe even 18 or maybe even 20 megawatts by the end of this decade. For reference, here's the Washington Monument. This is drawn to scale. These things are taller than the Washington Monument. They're really, really huge. This is the Airbus 380, the world's largest airplane, dwarfed by the size of these wind turbines. Now this is a constructed diagram here. This is a power curve for a typical offshore wind turbine. So what we're looking at here is on this axis, we're looking at turbine power in megawatts. Again, 1 megawatt is 650 homes. And on this axis, we're looking at wind speed in miles per hour. So this shows how the power of the turbine varies as a function of wind speed. So it starts out as the wind increases from 0 to up to about 5 miles an hour. Nothing's happening. It's zero energy from this thing, 0 power. And that's because the blades aren't turning. The wind's not strong, the blades turn. Then you get to about 6 to 8 miles per hour. Suddenly the blades start turning. And very quickly the power ramps up. It increases dramatically because the power is actually proportional to the wind speed cubed. So you get a very rapid ramp up of the power until you get to a point of about 20 to 25 miles per hour. And then what happens is the wind turbine automatically starts reducing the pitch of the blades to maintain a constant rotation rate. And a typical rotation rate for these big turbines is about 8 RPM, about 8 revolutions per minute. Which you can see off in the distance, that looks pretty lazy. It takes about 7 seconds for the thing to go all the way around. It seems like it's pretty slow. But the blades are so long that the tip of the blade is moving at about 200 miles an hour. There's a lot of stress going on, about 200 miles an hour. So they basically throttle back the turbine to a constant level of power, constant rotation rate. until you get up around 50 miles an hour, and then they feather the blade, or the turbine automatically feathers the blade, and the braking mechanism is engaged, the turbine stops rotating, the blade stops rotating, and the power drops down to zero. And basically you're riding out the storm at that point. And as the winds eventually reduce down, then it'll start operating again. Now, the maximum power produced by this particular turbine, 6 megawatts, you can see up here, 6 megawatts on the top here. There's a particular name for that. It's called the nameplate capacity or rated capacity of the turbine. You hear people talking about turbines, they're always talking about the nameplate capacity. That's the maximum optimum range of power. But lots of times the winds are not in that optimum range. They're down here, or the turbine could be shut down. So there's something called the capacity factor. That's the ratio of the long-term, for example, annual average power produced by the turbine to its nameplate capacity. And typical land-based turbines have a capacity factor of about 30 to 40%. So on average, they're only producing about 35% of their nameplate or rated capacity. But offshore wind turbines have a much higher capacity factor, typically about 60%. That's because the winds offshore are much more consistent and steady than winds on land. That's one advantage. Another advantage of moving to offshore. Two big advantages are higher capacity factor because the winds are much steadier, generally a bit stronger over the ocean. And also you can make the turbine so much bigger because you can transport them by sea. So there are basically two broad classes of offshore wind turbines: fixed bottom and floating. You can see the fixed bottom turbines are basically attached directly to the bottom, whereas the floating here float and are tethered to the bottom by some mooring system. Well, fixed bottom turbines only work out to water of about 60 meters depth. And as a result of that, they are not going to be a player in California. The water is just too deep here, it drops off too fast. In fact, fixed bottom turbines, which are very common along the East Coast, there are quite a few off New England, quite a few in Europe, they're not going to be a player in California because the water is just too deep. So it's going to be a floating platform, and there are essentially 3 different types of floating platforms based on the structure of the substructure. This is called tension leg platform. This is one you would put in place if you want to keep the turbine really fixed in one location as opposed to moving around. But the tension leg platform has lots of problems. It's unstable until it's deployed. It probably wouldn't work well in the Morro Bay area because the water's too deep. So that's not going to happen. We cancel that one out. The other is a spar buoy. The spar buoy is great in regions of very heavy winds and heavy seas. It could easily withstand a major hurricane running over the system. But the problem is the draft is very deep, and you have to have a very deep harbor to be able to tow this out to where you need to be. So basically, I don't think we're going to be having any of these. In fact, what I believe is almost certainly going to be deployed in the Morro Bay wind farm is going to be the semi-submersible structure, which looks something like this. Almost certainly it will be a semi-submersible substructure with a catenary mooring configuration. So what the heck is a catenary mooring configuration? Well, it's something that looks like this. Here's the turbine, and you have basically 3 lines, long lines coming down. Usually about twice or maybe 3 times the water depth total length here. The upper part of it is a synthetic rope, like a big thick nylon rope, and the bottom part of it is heavy chain, and that terminates at a drag embedment anchor. A drag embedment anchor looks like this. It's basically an angled plate of steel, which is embedded into the bottom by tugboats pulling on it, and it embeds itself down to about 30 feet into the ocean floor. The average length of mooring line will be about a mile for the wind turbines at the Morro Bay project. So a lot of mooring line along. There's something we need to think about. It's called a watch circle. When you moor these things in place, they don't stay exactly fixed. There's a nominal location where you kind of, if the wind wasn't blowing, that's where it would be. But when the wind picks up, they move around. So for example, this is the coast of California, and the wind is blowing out of the north. This turbine would migrate down to the southern end of its watch circle. The wind changed and blew out of the south, and would migrate up to the northern end of its watch circle. And the diameter of the watch circle depends on the water depth and mooring design. In the case of the Morro Bay project, the watch circle is going to be about 2 or 3 football fields. So these things are going to be moving around as the wind changes. Really dynamic. This is what things look like subsurface. The black lines here are the mooring lines. First of all, the turbines are typically about a mile apart, and that's about how it will be in the Morro project. The black lines here are the mooring lines. These are the dynamic array cables. The dynamic array cables carry the electricity. They link all the turbines together in lines of turbines deployed out there. Then they all gather up at a floating offshore substation, and then electricity is gathered together. The voltage is doubled up to from 66,000 volts up to about 132,000 volts. And then it's brought ashore by something called the export cable, which is subsurface. It's embedded below the seafloor, entrenched above the seafloor. Comes ashore to an onshore substation, and ultimately out to the grid where people can use it. Now, in the case of the Morro project, there's a decommissioned power plant at Morro, a lot like the decommissioned power plant at Moss Landing, and that's where the power will come ashore. From there, it will go out to the grid and be available to everyone. These lines are pretty hefty. This is what I was talking about, the synthetic rope. This is what it looks like. You can see how big it is, pretty thick. This is what the dynamic array cables look like. You can see again, pretty thick. Here's an array cable in cross section. So these are the three conductors here for the three phases of electricity. This is heavy armoring around here, insulation in the middle. There's a fiber optic cable right there, which allows the wind turbines to talk to each other and also be controlled from shore. This is what a floating offshore substation might look like. This is an artist's rendition. The one for Morro would probably be bigger than this, but it would look something like that. So what's it take to deploy something like this? Well, there are pretty significant port and infrastructure requirements for a floating offshore wind farm. First of all, you got to have a wharf with room for putting the turbines together. You need about 2,000 feet of waterfront access and about 6,000 pounds per square feet of pier strength. So you need a hefty pier there. You need a heck of a big crane, about 700 feet high and about 1,000-ton lift capacity, because basically you're going to be using that crane to assemble the wind turbine right at the water's edge here. I think it's going to be towed out. You need an upland yard here to a couple hundred acres to store the components. You need access to open sea. You need a channel deep enough to tow the turbine out to sea, because it's basically assembled at pier side, and then tugboats are going to tow it out to where it needs to be, and it's moored in place. You need moorage access vessels, tugboats, crew access vessels. A nearby airfield for helicopter access. It turns out a really good way to get people up there to do the maintenance is by a helicopter, and it looks something like that. Now, I got to tell you, when I'm looking out here, I'm seeing a lot of people saying, this looks like a lot of fun to me, I think I want to try this. Well, if you do, make sure you've got a really good helicopter and a really good helicopter pilot, because I think this looks pretty tricky, particularly if the wind is blowing. But that's what they do. When there's immediate maintenance required, they'll fly folks out there. They'll winch them down onto the top of the nacelle, they'll do their job, and the helicopter will come back and bring them home. So what's the cost to deploy something like this? Well, here's a breakdown of cost. The most costly items are the turbines themselves. It's about a quarter of the project. The substructure and foundation, things they float on, again, about a quarter. And finally, the electrical infrastructure, all those cables below, about 18%. Surprisingly, assembly and installation is actually not that large. It's only about 8%. So what's this Morro project going to cost in terms of implementation? Well, I'm estimating about $15 to $20 billion. This is a really big deal. This is an enormous project. And that's just the upfront cost. That's not the operations and maintenance costs over the 25-year life cycle. But the great thing about wind farms is their operation and maintenance costs are really pretty low compared to, say, a coal-fired or a gas-fired plant, because the fuel is free. And it comes to you automatically. It's the wind. It's free. You're just basically maintaining our wind. So what's it going to cost? What's the power going to cost? And how does it compare to other sources of energy? Well, the thing to use for that is something called Levelized cost of energy, LCOE. And levelized cost of energy is sort of a cradle-to-grave measure of the cost per unit of power that allows a comparison of different methods of electricity generation on a consistent basis. It includes the total implementation, operations, maintenance, and even decommissioning cost of a power plant. LCOE can be regarded as the minimum constant price at which electricity must be sold in order to break even over the lifetime of the plant. So it's sort of a cradle-to-grave grade cost of power generation. Then consistently compare different sources of energy. And what we see here, and it's plotted here, by the way, in terms of cents per kilowatt hour, which is kind of what appears on our PG&E bill. What you see here is offshore, or I should say onshore wind. Onshore wind turbines is the cheapest. In fact, it is the cheapest energy in the history of the world. There has never been a time where we've had cheaper energy than what we're getting now from onshore wind turbines. When you adjust for inflation and all that, go back to the early days of industrial revolution, cheapest energy in the history of the world. Pretty soon it's going to be surpassed by solar. Solar is number 2 here, but solar energy is dropping fast. Wind energy is dropping, still dropping as economy of scale, but solar is dropping even faster because of the technology. So pretty soon solar will become the cheapest energy in the history of the world. At about, right now it's about 5 cents per kilowatt hour. Followed by natural gas, geothermal, offshore wind, pretty expensive compared to onshore wind, about twice as expensive. I'll come back to that. Coal, and finally nuclear. Nuclear sticks out like a sore thumb. It is by far the most expensive power on the grid, and it's increasing, unlike the green energy down here, the costs are going down. The cost of nuclear is going up. So why is onshore wind or offshore wind so expensive? Well, it's about twice, right now, about twice as expensive as onshore wind. This is mainly because offshore wind has not yet achieved the economy of scale associated with onshore wind. As offshore wind farms are built out to utility scale is defined as 600 megawatts or greater. The biggest ones up there now are only about 50 megawatts. Their costs will decrease and approach those of onshore wind farms. It's supply chain and economy of scale and that sort of thing. So what are the examples of offshore floating offshore wind farms? Again, they're fixed bottom, they're floating. We're really talking about floating wind farms here. There's lots and lots of fixed bottom offshore wind farms out there, but there are only 2 operational floating wind farms in the world. Now, there are a number of individual kind of one-off R&D floating wind turbines that have been deployed by various companies and so forth around. But in terms of operational floating wind farms, there are really only 2. And the first is Highland, Scotland. It was the world's first large-scale floating wind farm deployed off the coast of Scotland in 2017. 5 floating turbines producing 30 megawatts of electricity. And the second is Windfloat Atlantic, deployed off the coast of Portugal in 2020. 3 floating turbines producing 25 megawatts of electricity. These wind farms are really, really, really modest compared to what we're talking about in Morro Bay. We'll see that in a minute. So let's talk about the specifics of the planned Morro Bay wind farm project. Well, first of all, where is it? Well, here's a depiction of where it is. Here's Morro Bay, down here. Here's Cambria. Here's Lucia. And the wind farm area is actually this hatched area where these lines are drawn like this, these diagonal lines. Never mind the colors here, don't worry about that. Those are different proposals that were came forward. But the final chosen area is, in fact, this hatched area with these diagonal lines. So don't worry about that right there. This is the wind farm area. This blue area here is the Monterey Bay National Marine Sanctuary. And you can see the wind farm abuts the sanctuary, but does not go into the sanctuary. It's called the Morro Bay Project because the power is going to come ashore of Morro Bay, but really it's off of Big Sur between Cambria and Lucia, about 20 to 30 miles offshore. It's about 399 square miles, so it's pretty big, almost 400 square miles. So what about the capacity of this wind farm? Well, there's enough room out there for 350 to 400 turbines, so I split the difference and said it's going to be about 375 wind turbines, spaced about a mile apart, each with nameplate capacity of 14 megawatts. We learned earlier that's that maximum power, generating up to about 20 amps of 60 cycle 3-phase AC electricity at 66 kilovolts. Now 14 megawatts is actually pretty conservative. There's going to be 14 megawatt turbines on the market within a year or 2. By the end of this decade, when this thing will actually be deployed, there probably could be 16, 18, maybe even 20 megawatt turbines. But I'm going with a conservative number here of 14 megawatts. Now, with a capacity factor of 0.6, which we learned about earlier, this wind farm will produce, on the long-term average, about 3,150 megawatts of power, which will make it the highest capacity power plant in California by far. A typical nuclear power plant, like Diablo Canyon, for example, is about 2,000 megawatts gigawatts. This is another 1/3 above that, which means it's going to produce enough power for about 2 million homes at a likely cost by the end of the decade of about 4 to 6 cents per kilowatt hour, which is very competitive with what we pay now. And most importantly, replacing the electricity previously provided by gas-fired power plants, this wind farm will prevent the emission of over 300 million tons of CO2 into the atmosphere over the course of its 25-year design life. Here's a rough timeline. I stress the word rough here because I made a lot of stuff up. In 2021, the project was approved by the Biden administration. That just happened a couple of months ago. Basically, the Department of the Interior gave the go-ahead. And in 2022, next year, the Department of the Interior will auction off the rights to develop the wind farm. That's basically the leasing process. As I understand, there are about 14 companies currently expressing interest. Then, from 2022 to 2026, I'm assuming 4 years, but it could be longer. It could be as long as 7 years. That's happened before. We'll be into the design and permitting phase. So basically, the companies that lease the area, and it might be more than one company. One company might lease the northern area, and one company might lease the southern area. They will come forward with design and ask for the government to give them a permit to proceed with implementation. That's when the public will be able to weigh in and public comment periods. I'm sure there'll be lawsuits, people will be suing. Federal judges will here and there. Project may occasionally be stopped and later go on. But I'm taking the optimistic viewpoint that will play out in about a 4-year period. So that means the deployment will begin in about 2027. I'm estimating it would take about 3 years to complete. So it would be fully operational on the power grid by 2030. Would help the Biden administration reach its goal of achieving 30 gigawatts of offshore wind power by 2030. By the way, a gigawatt is a million megawatts. So for example, this is 3,150 megawatts, so that's 2.1 gigawatts. So this wind farm will be about 10% of what the Biden administration is trying to achieve by 2030. The design life of the system is going to be about 25 years. So by about 2052, you begin replacing wind turbines at the end of their 25-year design life. So possible issues of concern. Whenever you feel something big like this out in the ocean, there are going to be issues of concern. There's no doubt about that. So I'm going to try to talk about those. The way I see it, there's sort of 4 areas of concern. Impact on commercial fishing, impact on whales and dolphins, impact on seabirds, impact on the Big Sur Viewshed. So we'll run through these. Impact on commercial fishing. Commercial fishing will be banned within the entire 399 square mile area of Monterey wind farm, as towed nets would be in jeopardy of becoming entangled in all of the mooring lines and array cables in the water. On the positive side, the wind farm will effectively serve as a very large marine protected area and a habitat for many types of fish. Thus, it will help rebuild and sustain fish populations in the surrounding waters. In any case, the Pacific Coast Federation of Fishermen's Associations has come out in opposition to the Morro wind farm. Now, let me say this about fishermen. I have a great deal of respect for fishermen. They put food on our table. They pursue a very dangerous profession, and their voices need to be heard. That's certainly true. The next area of concern is impact on whales and dolphins. And there are 2 areas there that I think are the ones that stand out. Possible impact of noise in the water from the turbines, and possible impact of electric and magnetic field emissions from the dynamic array cables that don't carry all that electricity. Now, this is a depiction of the migration path of gray whales off our coast. Here's Monterey right here. Here's Lucia, here's Cambria. Most of the whales, of the gray whales, migrate within about 6 or 7 miles from shore, kind of in this region right here. But some can be found as far offshore as this. And how does that compare with the wind farm? Well, the wind farm is right here. So it's inevitable, although it's not really going to impact directly most of the whales that are migrating. It's inevitable that some whales are going to find themselves transiting this wind farm. Inevitable. And so what are the impacts there? Well, the first area of concern is noise put into the water by the turbines. So basically, as the turbines the blades are rotating, there's bearings and lots of machine noise going on here. Those vibrations are going to be transmitted down the tower inevitably and into the floating substructure and then out into the water column. There's no doubt about that. There's going to be some sound given off it. So the question is, how loud is it and how is it going to affect the whales? Well, kind of estimate that. First, let's take a look at undersea sound sources. Now, things are getting really technical here, so bear with me. What we're looking at here on this vertical axis is noise level in decibels, which are usually referred to as dB. And so as you go up this side here, as you go up this axis, the noise is increasing. And on this axis here, we're looking at frequency of the noise. So the left-hand side, that's low frequency, would be like a really, really low note. And on the right-hand side, that would be really high frequency, would be like a higher pitch note. So we can see up here, the loudest undersea source of noise is undersea earthquake. It's way up here, lots of noise, followed by a volcanic eruption. This would be sonar, a Navy sonar, or a seismic air gun array used by the oil industry to prospect for oil. Here's a blue whale, lower frequency, but it puts out quite a bit of noise, comparable to a supertanker right here. Here would be sort of a mid-sized Navy ship. This is an offshore drilling rig, an oil platform. And then you have various whales, humpback, bowhead, a pair of dolphins down here. Here's a sperm whale, dolphin down here. This is submarine, pretty quiet. This would be the sound from distant shipping. So where's the wind turbine come into play? Well, roughly, again, very roughly, based on me just looking at a few papers, to kind of fall right in here, it would be something like a drilling rig but quieter. It would be between a submarine and a drilling rig, and kind of in that lower frequency range, but it would be within the hearing range of whales. This is the hearing range of a fin whale, which is probably pretty characteristic of this whale. And you can see that they can hear lower frequencies that would be produced by the wind turbine here. But they're not, it's not large, it's pretty quiet. In fact, it's pretty comparable to what whales, the noise that whales themselves generate. In fact, even quieter, much quieter than a blue whale, for example. So, that's kind of where we're going. The next area of concern is electric and magnetic field emissions from electrical cables. Now, here again is the cross-section of one of these array cables. And the thing about it is, it's very well insulated. It has a strong shielding system here. It's also very well grounded. So I'm not worried about electric field leaking out of this cable. That's not the problem. The problem is that you can't shield the magnetic field. As the alternating current is switching back and forth inside these cables, the electric field is being contained within the cable, and that's kind of shown here. It's not leaking out. But you can't contain the magnetic field. So there's a fluctuating magnetic field around these cables. And that fluctuating magnetic field is impinging on seawater. Seawater is the conductor. Whenever you have a fluctuating magnetic field impinging on a conductor, it produces an electric field. That's how a generator works. So there will be an induced electric field parallel to the cable by this magnetic field. I don't think there's any way around that, because matter of fact, you can't shield that magnetic field. But it's going to be very weak, very, very weak. Take my advice here, 10 to the minus 5 amps per meter squared, 10 meters distance, that's really weak. So for example, if you were a diver, and you came up to this cable and put your hands on it, you wouldn't feel it. You're not going to experience anything. Although if you had an instrument, as far as a few tens of meters away, a sensitive instrument, you would be able to measure the electric field. If you were a shark, you would experience this. Sharks are very sensitive to electric fields, and sharks would probably exhibit avoidance behavior associated with this. Impact on whales. I don't know of any cases where whales have shown avoidance behavior pertaining to undersea cables, undersea power cables, or offshore wind power cables. But this is something to think about, something that probably needs to be looked at more, needs to be more research done on this. Just want to point it out as an area of concern. Impact on seabirds. Millions of seabirds exist off the coast of California. It's about almost 1,000 species, I think. And the area that will be an occupied wind farm is certainly part of their habitat. Unfortunately, wind turbines kill birds, but there is available technology to reduce the number of kills. For example, there is bird detection radar, which can see a flock of birds 3 to 5 miles away, and it can automatically shut down the turbine. It looks like they're going to impinge on the turbine. That's used routinely at onshore wind farms. It also has been used in the offshore wind farms. This is the one in Scotland. And also, recently, they discovered that just simply painting one of the blades black, which produces kind of a strobing effect, allows the birds to more recognize that there's a turbine there. And that's actually been shown in land-based turbines to reduce bird kills by about 70%. So that's something that can be used. And finally, unlike other birds, seabirds tend to fly close to the surface. And most will likely fly in the air gap below the rotor blades. So for the turbines that I'm expecting will be deployed in Norway, it's going to be about 120 feet from the surface up to the bottom tip of the blade. I think most of the seabirds will be flying below the rotor blades. In any case, the bottom line is the Audubon Society supports offshore wind development, recognizing that climate change is killing many, many birds each year, and that offshore wind power is part of the long-term solution. So the final area of concern is impact on the Big Sur Viewshed. Now, here's the only equation in this whole talk, so don't get mad at me for showing it. It's a handy-dandy equation here that says the distance you can see something above the horizon over the ocean is given by, in miles, is given by this expression where h is the height of the something above the sea surface in feet, and h, small h, is the height of your eyes above the sea surface. Well, in the case of Big Sur, if you're driving on Highway 1, you're typically in elevation about 400 feet on Highway 1. And because these things are so huge, up high about at least 600 feet, the upper two-thirds of the turbine's power would be visible at the horizon at a distance of 42 miles offshore. And of course, the wind turbines are only 20 to 30 miles offshore. What that means is the turbines will be visible from Highway 1 under optimum viewing conditions, but you're going to have to look hard to see them, because they're going to appear as specks on the horizon. And what optimum viewing conditions means clear sky, clear air, no haze in the air. It means no glare off the water. So to be able to see them, it's probably going to be in the morning on a very clear day. Afternoon, it's hazy, forget it, you don't want to see them. Afternoon, probably not going to see them because too much glare off the water. So this is actually what it's going to look like. This is simulation produced by the Bureau of Ocean Energy Management. So this is the view with the naked eye, simulated morning view of the Morro wind farm from Pfeiffer burns with the naked eye. So if you look carefully here, you can see these dots right along the horizon. That's the northern edge of the wind farm. You have to look pretty close, but you are visible with the naked eye. If you have a modest pair of binoculars, it'll look like this. You'll actually be able to see the blades turn from Julia Pfeiffer burns. You'll probably be able to have a view similar to this from the Peninsula with binoculars. So, in summary, we face a climate crisis that is growing worse by the year. Offshore wind power is a key technology for reducing CO2 emissions and mitigating this crisis. The Morro Bay offshore wind farm was recently approved by the Biden administration. Deployment of this massive wind farm, keyword here is massive, will likely begin in about 6 years and be complete by 2030. It will become the largest capacity power plant in California and produce enough carbon-free electricity to power at least 2 million oversized homes and prevent the emission of over 300 million tons of CO2 into the atmosphere over its 25-year design life. Although there are areas of concern, in my judgment, none of these concerns are showstoppers for this project. You may come to a different conclusion, and that's fine. I just wanted to kind of give you the information to make such a decision. I believe the Morro Bay wind farm should be deployed, and that its successful implementation will serve as a model for other offshore wind projects in the U.S. and around the world aimed at fighting climate change. That's it. Thank you very much. Thank you. I have a question.
Yes. So if you're sailing from here to Hawaii, start opening up the water, how do you see it? That would be the first round. Will they have this vessel identification system, ALS? How do you see them?
Well, how do you see them at night? Yes. Great question. Great question. Yeah, hazard navigation. That's a good point.
Hazard navigation.
Yeah, right. They will have lights. They will have lights on them. You know, like.
Will they have an electronic signal?
I don't think they'll have an electronic signal, but they will have a huge radar signature.
Okay.
You know, they're so tall, and there's lots of steel in them. You know, that they'll be visible on radar really far away. Now, does that mean the ship might not stray in there? I can't guarantee that won't happen, but if it does happen, that's a real failure of the ship's crew because they will be extremely visible, both visually with the strobing light and also on radar. Anybody else?
How much atmospheric turbulence is involved?
Yes, great question. I didn't mention it, but I did throw out they're spaced a mile apart. What really dictates the spacing is, in fact, the turbulence that Mary Alice is mentioning here. The turbines have to be in the sort of prevailing wind direction, downwind direction. They need to be spaced at least 10 D apart, where D is the rotor diameter. And in the crosswind direction, they're typically spaced about 8 D apart. Again, D is the rotor diameter. So as the turbines make bigger, you have to space them farther apart, and that's because there's a lot of turbulence that comes downstream of the turbine. You have to let that sort of sort out before the wind hits the next turbine, or else you're losing efficiency that way. Yes?
What determines the 25-year design life of this project? I mean, why aren't parts replaced, and after 25 years, is that whole project abandoned, or what determines?
I think that's basically the engineering design life of the turbines. There's a certain amount of wear and tear. Their bearings, because these things are, these blades are very heavy, they're turning for all those years. Certainly marine corrosion is an issue too. What the engineers say now is 25 years. And I don't believe the project will be abandoned. I believe you would be basically swapping out the turbines for a new generation of turbines at that time. Yes. Okay.
Is there something around the edge of it so that boats can't get too close, like I think the shore boats to see the turbines or something like that?
Well, that's a good question. I don't know the answer to that. Whether private vessels will be kept out of it. I think the answer is probably going to be no, that they would be able to go in there. But there certainly will be restrictions on fishing. Certainly commercial fishing, maybe even pleasure fishing, I'm not sure. Yes?
Is there significant power generation during the night, or because the onshore winds still blow during nighttime?
Yeah, that's the big advantage of offshore wind turbines. Over land, of course, at night the wind tends to die down. That's because the land surface cools down, and the atmospheric boundary layer, the lower part of the atmosphere, becomes stable and sort of decouples from the upper atmosphere when it's still blowing stronger. But over the ocean, you don't get much of a daily variation in the sea surface temperature, and so night isn't very much different from day. And so that's one reason why the offshore wind turbines have a high capacity factor of 0.6 compared to only about 0.3 to 0.4 for onshore. Winds are much more consistent offshore through the night, which is good because we want to complement the solar. We obviously need solar power at night, and so the fact that these offshore wind turbines still do generate a high degree of power during the nighttime, that helps supplement the solar. Yeah.
I heard that GE just came out with a real biggest wind turbine that they've ever built in the world.
Yeah, it's called the Haliade X, and it's a 12 megawatt turbine. And I think they've only built one so far. It's a prototype. The Chinese just came out, kind of one up some of the trip. They just came out with it's a company called Mingyang Sustainable Energy. I just saw the news last week. They come out with a 14 megawatt turbine. So it keeps getting, keeps going up like that. So it'll be competition. By the way, I think what's going to happen once this project goes forward and is approved, I think GE will probably, and perhaps some other companies will open a factory on the west coast of North America. I would guess. Because right now they manufacture the turbines in France, mainly because most of the market is in Europe. But once this thing is clearly going to go, I think there's going to be a market for building these things on the west coast. Whether it's in California, whether it's in Mexico, or Central America, I don't know. But I expect that there will be manufacturing happening on the west coast. Yes?
So the assembly plant for all that work?
Oh, I'm glad you asked that. Yeah. I'm just guessing, I don't have any inside view here, but I'm pretty confident that the assembly point is going to be Port Manimi. Port Manimi is down in Ventura County, about 40 miles south of Santa Barbara. And I think it meets all the criteria for this thing. It's about 150 nautical miles from there to the actual deployment site, but that's kind of as close as you get. If Port Manimi doesn't work, then I think you're going all the way down to Long Beach, which is pretty far south. What about Port of Oakland? Well, the problem is that Oakland Bay Bridge, you can't tow the turbines under it. It's way too low. So I think it's probably going to most likely be Port Navy, and with a backup maybe being Long Beach. Yes. About 80 tons. They're about 80 tons a piece. They're pretty hefty. They're huge. I didn't show the picture of one compared to people, but they're really big. They're made out of carbon fiber, a continuous thing of carbon fiber, and that's the limiting factor. You can't transport them by land, you got to transport them by sea. Yes.
On an earlier chart where you showed the percent of conditions, what is the
Keeling curve, yes. There was an oceanographer by the name of Charles Keeling down at Scripps Institution of Oceanography down in San Diego, who I guess it was in the 80s or so, conceived this project with some of his colleagues to start making very detailed measurements of CO2 in the atmosphere in Hawaii. And that was he was the first person to really show there was a seasonal cycle and to make very detailed measurements showing how it was increasing every year. So in his honor, it's named the Keeling curve. He was the first person to really make very detailed measurements of CO2 in the atmosphere. He received the National Medal of Science for that work, and he's honored by the Keeling curve. Yes, Michael.
What is the statistics from Europe with the effect of the
What's the experience? What was the experience?
The European statistics on the effects of the internal.
Yeah.
I'm sure there are.
I haven't seen any negative issues there. For example, thinking about the impact on whales. There's nothing I've seen showing that's been a big problem there. On the other hand, I don't believe any of the wind farms over there have been deployed in whale migration areas like we have here, so that's an issue. As far as other environmental effects are concerned, I haven't read anything negative. I can tell you that fishermen don't like offshore wind farms. There's lots of big fights occurred on the East Coast when when wind farms began springing up off the coast of Massachusetts and throughout that area. Because basically they're being forced to give up real estate for which they would be fishing in. Also impacts their transit. They have to go deeper water, they have to go around the wind farm, those kind of things. Yes.
The impact of a governor in California doesn't do the climate change.
That would not be good. Governor Newsom has come out very strongly in favor of this when the announcement was made by the Biden administration. He concurrently, made the announcement. He was really pushing for it. The wind farm will be in federal waters. It's 20, 30 miles out. So the state jurisdiction extends out 3 miles. And of course, there's the Coastal Commission that deals with what's happening right at the coast. Now, the only thing that's going to impact that is going to be the export cable. The power is going to transit through the state waters across the coastline. So the Coastal Commission in the state is involved there. But the wind farm itself is in federal waters within our EDC. Yes.
How does the electricity get from the homes or from the substation where the megawatts are stored in the wind project to the homes? How does that?
Well, it goes right onto the river, and that's the advantage of bringing it ashore at Morro Bay. Morro Bay is kind of like Moss Landing, and you probably saw the article about the big battery storage system at Moss Landing. The world's largest battery energy storage systems at Moss Landing. And the great thing about that is all the connections to the grid are there. So they just basically piggyback on that. And that's exactly what we're going to do with this project. All the connections to the grid are at this Morro Bay decommissioned power plant, and it'll just plug right in. I agree with you on that. The existing nuclear power plants are so-called second and third generation power plants, and they have a lot of problems, and I could talk for a long time on that. But there are on the drawing board fourth generation power plants. Bill Gates talks about that quite a bit in his book, which is very good. And those fourth generation power plants significantly mitigate, not completely eliminate, but significantly mitigate the big problems of existing nuclear power plants. Existing nuclear power plants have the problem of possibility of catastrophic failure, which is going to not necessarily kill a lot of people, but it's going to render them about 10,000 square miles of real estate uninhabitable for centuries, not a good thing. What do you do with nuclear waste? There's no good solution right now. For a long time, the answer was going to be Yucca Mountain and Nevada, and that got put on permanent hold. So we don't have a good solution for what we do for waste. The third problem is if you own a nuclear power plant, then you have a path to nuclear weapons. Now, I'm not worried about PG&E developing nuclear weapons and attacking Florida Power and Light. Although, given the division in our country, who knows? But there are rogue countries out there, for example, North Korea. North Korea has about 2 dozen, by most accounts, nuclear weapons. And those have all been produced by reprocessing the fuel rods from their nuclear power plant into plutonium. The Israeli Air Force has acted twice, once in Iraq, once in Syria, to blow up nuclear power plants because they feared that they were going to be used to produce nuclear weapons. So those are the problems of existing power plants. The fourth generation designs, which exist on paper, there's about half a dozen designs existing on paper. There are also a handful of small test reactors that have been built. They significantly mitigate those problems. They don't completely eliminate them, but they significantly mitigate them. And China has announced plans to field at least one, perhaps two operational fourth generation plants by the end of this decade. So yes, they may indeed be part of the solution. Yes?
How do we so far out to come in?
Say again?
You're really far out.
Yes, about 30 or 40 miles out.
And is there like a power loss to the line?
Oh, power loss, yeah. Well, that's why they crank up the voltage so high. You know, we transmit power on the U.S. power grid, you know, all across the entire western United States, for example. And the way that works is the voltage is cranked up very high. The higher the voltage, the less power loss. And that's why they crank up. The power coming from turbines is 66,000 volts, and the power going into shore is 132,000 volts. That's kind of the standard. And that voltage is high enough that there's minimal power loss. Yes? Yes, there's no shipping lane that goes through them. And that doesn't mean a stray ship isn't going to go find some, lane to go through them. But there certainly will be, notices from mariners and charts that clearly indicate the wind farm. And then we talked earlier, it's going to be flashing lights. It's going to be a huge radar signature there. So I'm not too worried about, that sort of thing. Yes? I'm not aware of that. People have talked about so-called small modular reactors as a solution to climate. And a small modular reactor is basically the kind of nuclear power plant you would have on a submarine. And you could actually transport your components by land, and they're simpler and much less complicated and presumably much less prone to failure. So there was a proposal to have many small modular reactors developed, and that would be a solution to replace the large, giant power plants. But that's never gotten beyond the talking design phase. There's currently, as I understand it, there's no plans to build any, and that's not going to go forward. Yeah. Yes. Well, actually, the announcement that came out from the administration and then the Governor Newsom supported also included a wind farm off Humboldt, smaller than Monterey Bay. And I haven't really dug into that much because I was focused on the local area, but there is in parallel approval for a project up off Humboldt Bay. The winds are better up here, that's true. Yeah. Yes? Yeah, I don't know the exact value of it, but you're quite right. There's an awful lot of turbines there. They've been there for a long time. They're kind of smaller. Yeah, to kind of, yeah, but I can understand that, yes, that makes sense. But I don't know the part, but nationally, we get about 8% of our electricity from wind, and it's growing every day. Yes, yeah.
What's your opinion about China's attitude? My impression is that they often believe in
Yeah, China's a mixed bag. China's a really mixed bag. First of all, as you saw on the chart there, they're the world's largest emitter. You think, well, I really meant Chinese. But then you think about it, China is also the world's largest country, most people. And if you look at per capita emissions, they actually fall pretty far down the list. They're kind of in the middle of the European countries. We, the U.S., are number one. So China's kind of a mixed bag. China's actually bringing on green energy faster than any other country. That's the good news. The bad news is they're also bringing on coal-fired plants faster than any other country. So they're off the scale on the good side, they're off the scale on the bad side. Kind of mixed bag. Basically, in the case of China, they are just super energy hungry. They want more and more energy because they want to raise their standard of living. And the way to do that is more and more energy. And so they're a mixed bag, both on the positive and negative side. I wouldn't be surprised, I don't know the specifics of that, but in his book, which I highly recommend, it's How to Avoid a Climate Crisis, he talks about fourth generation plants, and he does it, he's very upfront, and he's an investor in at least one company that are, developing this plant, so he may have been part of it.
How about that? We just go home right there, and we question.
Sure. Sure.
So